Okay. So happy Friday, everybody. It's the weekend. Let's get started and do some recap to bring everybody up to speed as you eat your wonderful cookie that Brittany offered. Okay, so we are almost done with this. I still have to talk a little bit about six figures, so this is grayed out for you. But let's try to remember the difference between accuracy and precision. So what does accuracy mean? What does precision mean? Anybody? Go ahead, Ingrid.
So accuracy is probably yes.
Very good. So that's excellent. So to repeat what Ingrid said for the recording, so accuracy is how close our mean is to the true value or a reference value. And how do we assess that? What's the statistical measure we do to assess accuracy? What is it called? Percent relative error. So we get accuracy by calculating percent relative error, and precision is how close our data, the replications of our data to one another. So we just got, I don't know, you guys in the back, you know the students, right? So this is Taylor, Medora just walked in, Katerina as well, right? Okay. And precision is measured by what? How do we assess precision? By what statistical measure, Ash?
Standard deviation.
Standard deviation, and the better one would be coefficient of variation. Who said that? Ruthra. So coefficient of variation because why? It corrects for what? Remember? Yes.
The mean and then
Carol, it corrects for the size of the mean. Yes, correct. So if one, like we gave example of percent protein in flour is 12%, and in a protein isolate is about 90%. So there is a huge difference between a size of a mean of a 12 versus a size of a mean of a 90. So when we correct for the size of the mean and we get a percentage, that gives us a better idea about the precision of that particular experiment. So in the lab, when we analyze data, we always ask you to calculate percent coefficient of variation and not just standard deviation. What's the difference between threshold and sensitivity? Who wants to give that a go? Go ahead, Snow.
the threshold is your detection limit, and the sensitivity how small the difference in the
Yes. So to repeat for the recording, threshold is how low of a measurements we can detect, so our detection limit. And sensitivity, how small of a difference between samples we can detect using our method. So that indicates sensitivity. So in what case, CB is better measure of precision than standard deviation? So we just answered that when we have different sizes or means that vary in how big or small our means are, we correct for the mean using the coefficient of variation. So what is meant by systematic error compared to a random error? Can you give me an example? Go ahead, Kevin.
Systematic error would be something in all your data, so like a scale.
Very good.
Error would be something that random.
Yes. So systematic error, something that is something that you don't have as an experimenter, you don't have control over. So either you're using a pipette that needs calibration, or a balance that needs calibration, or even a pH meter that is out of whack, that consistently giving you an erroneous result, consistent and systematic. So the same error across all of your measurements. Random error can be anything, and every person running a lab have their own experimental error. That's why in statistics, when you learn, there is the true variation versus variation due to experimental error. Every experiment is associated with a particular error. Give an example of a blunder type of error, something that completely mishap. Go ahead, Ash.
I think that the example you gave last time was like titrating with the chemical, like you use sodium hydroxide instead of hydrochloride.
Absolutely, titrating with the wrong reagent or preparing a wrong concentration, doing a calculation error instead of preparing a 0.1 molar NaOH, you prepare the 1 molar NaOH, that ruins the whole experiment. So that is a blunder, and we're all prone to blunders. Nobody is immune of making big mistakes at times. Okay, so we'll carry on and talk about significant figures. This is going to come across or come around a lot during our experiments. And we try to kind of give you the general idea of a significant figure. And then later, for every experiment, when it's time to write your report and put your data in table, we'll guide you in terms of how many significant figures your data should have in the table. You do not want to put infinite numbers of digits or 10 numbers after the decimal points. So you want to figure out how many numbers that would be significant figures you want to include in your average. And you want to make sure your table has all of the data in the table have same numbers of significant figures. So I'll start by giving you, I know that you've taken this in the past somewhere in your high school and even here. So we'll just try to remember some general facts. Okay, so if you have a number, let's say 700, how many significant figures are there? Brandon, 1. Brandon, what did I call you Brandon for? Sorry. Okay. And if you have, how many significant figures do you have?
3.
3. Yes. Thank you. So when I have a decimal point and I specifically include these 2 zeros, that means I am certain of those 3 figures. I'm 100% positive that this is the value. So if my balance, for example, reads to 3 decimal points, this number here is a rounded number. I'm not certain of it on my balance. I am certain that I'm weighing 1.00 grams, and this last number is rounded on my scale, so I do not report it in my final calculation. Okay. If I have 0.006, how many? Brayden, 1. Yes. Okay, so I have 1. In this case, anything to the left, even though there's a decimal point here, anything to the left is not significant. If I have a balance that reads to 5 digits, that's a very sensitive balance, and it reads to 5 digits after the decimal point, I am certain up to here, and this is rounded, so I can report 2 significant figures in this case. Okay. If I have a 5.01, how many significant figures do I have? 3. Yes, thank you, Sarah. Okay. And same goes if I have 64. Okay. 72. How many do I have? 4. Okay, it's perfect. So this is simple. You all know your stick figures, so that's great, but this doesn't end here. We will be calculating, we're going to be using addition, we're going to use division, we're going to use multiplication. How do we report our significant figures? So again, I'm going to give you examples of certain general rule. Let's do an addition. So let's say I'm adding to determine the average. So I'm adding 7.45 plus 8.725. And then I'm gonna get the value of 16.175. Okay, that's the addition you do before you average. So you want to follow the addition rule. So how many significant figures should my answer be? So I need to change that to the correct significant figures.
I would have to round the decimal.
You will have 2 after the decimal point. So you will report it as 16.80. That is correct. You apply that for addition and multiplication. When you have decimal point, you go with the lowest number of decimal points. So you would round the 75 into 8. Okay. So if I have multiplication, so if I have, let's say, I'm multiplying different set of numbers times 238 times 1.2, and I got a value of 9566.172. So here I have 4, here I have 3, here I have 2. So what would my number be here? If I want to report the correct significant figures. How many significant figures should my answer have? Medora, 2. Yes, okay. Perfect. So 2. So I'm just going to have to round here to 9600 and whatever is my unit. So now I have to. Okay. So I'm going to give you a real example, something that you would probably relate to in the HPLC lab. Okay. All right, so you have determined a concentration of caffeine to be in your sample, in your diluted sample, to be 43.5 micrograms per milliliter. And this sample has been diluted 50 times. So basically, you have used a volumetric flask, a 50 milliliter volumetric flask. You put 1 ml of your, let's say, Coca-Cola or any sample you are measuring caffeine in. You put 1 ml in 50 ml, so that's a dilution of 50 times, and you got this value. So you want to determine the original concentration. You take into account the dilution factor, so you would go, okay, 43.5 micrograms per ml times 50, because you have to be diluted 50 times, so you want to correct for the dilution to determine the concentration of caffeine in your original sample. So you get this value, 2175 micrograms per milliliter. Okay. Taking into consideration the significant figure rule. What will your answer, how many significant figures should your answer have? Your multiplication rule. 1. So you would go and say it's 2000 micrograms per ml. Okay, this is not good. I have reduced the sensitivity of my analysis by just disregarding this much of the concentration. All right, if I go back and tell you this volumetric flask is accurate 50 milliliter to 0.05 microliters, or I would say, yeah. So it's accurate to this far. Sorry, milliliters, not microliters. We're talking milliliters. Okay, so it's accurate to, so if when I put 50, it's either 50.05 when I reach out to here, or it is 49.95 milliliter in this range. So I added a level of accuracy. So I added to here 0.05. So basically, I added a second. So this is a rounded figure. Remember, the last digit is a rounded figure. So my accuracy is, so I have 3 significant figures now that I account for in my multiplication. So now, instead of 1, I have 3, because I am certain in this volumetric flask down to 0.05 milliliter, and the last one is rounded, so I'm certain to this first digit here. So then I'm certain to the 3 significant figures. Then instead of this, I go, okay, I can report that many significant figures. So now I enhance the sensitivity of my method. So in the lab, you'll be using different balances. You will be using different tools like mechanical pipettes, graduated pipette, volumetric pipettes, and all of them they're accurate to a certain decimal point. So this will help you in determining how many significant figures you're certain of and utilize that in your final answer. So we'll practice that quite a bit next week in lab. And for every lab, when you're running an experiment, you can ask me, the TAs, Kat, how many significant figures there should be and why. So we will guide you in that. But if you ask me, the main thing you want to remember is you don't want to clutter your table, your summary of data. You don't want to put so many figures and so many numbers after the decimal point. You have to be concise. You don't want to lose the sensitivity of your method, but you also don't want the clutter of numbers that you're not certain of. Okay, so this is the general rules, taking into account the sensitivity of the measurement tool that you use, and then the exception of the rule. Every lab will let you know if there is an exception to work with. Like if you are determining the average, so you are dividing, you have 3 replications and you're dividing by 3, it's always 1 significant figure. You don't follow the rule of a division. You just follow the rule of addition when you are adding, because getting the average is not necessarily, you need to take the significant figures of the average number, of the number of replication. So that's where there are some exceptions to the rules of division or multiplication. We will guide you in that. Okay, the last thing I want to mention is rejection of a data point. You might encounter that in some of your labs where you have multiple replications and then there is an outlier. You can feel it, you can sense it, like, okay, I'm measuring, again, caffeine. Actually, you will potentially face that in the caffeine lab because two groups, each will be preparing two replication and then you will be sharing the data. So two different groups are preparing the replication, so there might be a data point that is off because different people are preparing the sample. One person might have a blunder and the data point is completely off. So what you do in this case, you want to see if you can eliminate that data point. If you don't eliminate it, your precision will be poor, your accuracy will be poor. The way to determine if one data point is really out there and needs to be eliminated, like your 3 replication of your caffeine is giving you 40 micrograms per milliliter and one is giving you 20. It's completely half. Somebody just did a dilution error and you don't want to mess up your entire data set. So you go ahead and calculate Q. So the Q is, let's say you have X1 and X2. One of them, let's say X1, is the data point that you think is completely out there, wrong. It just looks really outside of the other data points. And you get the difference with the next data point closest to it. Let's say one is, let me just, okay, so you have a data set of 42, 45, 38, and then 21. All micrograms per mil, let's say the unit. You can see these are very similar, and this is way out there. So I can call this X1, I can call this X2. This is the closest to it. In the set of data, 38 is closest to 21. So I get the difference and then divide by the range of your data, which is 45, the highest minus the lowest. Okay? Then you get a Q value. Then in your book, page 57, there is a table for Q values. The table calls for number of observation. Let's say you have 4 replication. 1, 2, 3, 4. And then the Q of rejection at 90% confidence level is 0.76. If your calculated value is greater than 0.76 in that table, then you reject that data point. Then you can say, okay, I'm going to calculate the mean without this value. I'm able to reject it. Then your precision will be improved, your CV will be much better, and your accuracy will be much better. Any questions about the Q? You will potentially need it. Some groups will not need it, but sometimes if you really have this blunder and resulted in a bad replication, this is Q to the rescue. So it helps you improve your data. Okay, so next week, Monday and Wednesday, we will learn how to utilize certain tools in the laboratory. We're going to learn how to utilize analytical balance, mechanical pipettes, volumetric glass work. You might have all taken organic chem lab by now. These might be just a refresher, but we'd like to start with refreshing your memory of utilizing these tools. You'll be using them the entire semester. And while doing so, we're going to calculate precision and accuracy and reinforce the knowledge of precision and accuracy, which will also be with you the entire semester. Textbook is chapter 4, what I covered in class, and you're going to be using your lab manual chapter 6. Do you all have your lab manual, or do you still not have a lab manual? Any of you not having a lab manual yet? Quite a few. Make sure you email Pat before next week so that they can print out physical copies for you. Check in to make sure that the lab manual is on its way for you, but you do need it, a physical copy. We'll go over lab safety and sources of errors. You will find them in week 2 under lab material. The pre-lab quiz is already posted as an assignment, I believe. Yes, Brittany? Yeah, it's up for you. And you turn it in by 9 a.m. on the day of your lab. Remember, there are few of you that shifted to Monday. Make sure you remember that you're in Monday lab versus Wednesday lab. You bring your lab manual with you, your lab notebooks as well. You would need calculators unless you use your calculator on your laptop. And you all need your laptops. So, or pad or whatever you have, because you will be filling in an Excel sheet that I will share with you for the data. So you will be generating data and putting it directly in your Excel sheet, doing the calculation. Half of the lab report will be done before you leave lab next week. So make sure you bring that. And we will meet in the teaching lab, ABLMS 135. So the lab starts at 9:35 on your schedule, but if you're in lab at 9:30, that would be great to get settled, to get the lab code, to get your name tag, and get settled so that we can start on time. So please be mindful of that. Any questions before moving to the next topic? Okay. Sampling and sample preparation. So this is another very important introductory topic to analysis. When you go out to industry, whether you work in quality control or analytical lab, or just research and development in general, sometimes you really have to do some analysis before you get into your next step, whether it's production or R&D or just simple quality control. So you really need to understand how you gather a sample from a particular lot. How do you prepare it for analysis so that you can make an accurate decision? So this is really a very fundamental component or understanding of food analysis. It might not be as exciting of a topic, but it's a very important topic. All right, so let's see what you guys know. And I don't expect you to know, that's why you're here, but let's see what your guess would be. So to determine food quality and acceptance, it is essential, important to monitor the composition and characteristics of the whole lot of food product or raw ingredient. So you need to do testing on the whole lot. B, evaluate a sample or a set of samples from a lot, then decide to accept or reject a particular lot. So sometimes you have to kind of reject a whole lot and throw it away if there is a risk to the consumer or a risk to your reputation as a producer. Determine sample size, like how many samples you want to pull, and select a protocol for sampling based on factors such as the nature of the product. Is it a homogeneous product? Is it a heterogeneous product? How is it packed or packaged? And what's the purpose of the inspection? Is the purpose of inspection general quality control, consumer acceptance, safety? What is it? So where would your hunch be in answering this question? Yes, Taylor?
So B and C.
B and C, yes. So in many, almost 99.99% of cases, you cannot evaluate the whole lot. But sometimes you can evaluate the whole lot. Can you give an example? Can you think of something that you would test on everything that comes through?
I mean, you can always do metal detectors for everything.
Yeah. So you're running your flour through metal detector, your grains. So you can run the whole thing on a belt through a metal detector. It's non-destructive and everything can be screened. That's very small percentage of the type of products and raw ingredients that you can do such thing on. Okay, for sample preparation, prior to analysis, the following is true. So you collected your samples and now you want to prepare them for analysis. For all types of analyses, the particle size should be reduced to 20 mesh. First of all, do you know what the mesh represent? What does 20 mesh mean to you? 20 mesh. Yes, Sarah?
That's right, so that's like the sifter grain size that you order.
Yes, it is, but if you want to be a little bit more specific, when we say 20 mesh, that means there's 20 opening per inch, per linear inch. That's what it means, 20 mesh, that means there's 20 opening in a linear inch, 1 linear inch. So the bigger the number, the smaller the opening, that means the smaller the particle size you get. Often, you really need to have very small particle size for particular analysis. So we'll think about that in a minute. And then enzymatic activity should be eliminated or controlled. Lipid oxidation should be prevented. So what is your guess answer? Any guessing? Okay. You know, you get +2 even if you answer wrong, so why don't you? Okay, yeah, thank you.
B and C.
B and C. So it's a good guess. They got him +2, and it's the correct answer. Yay. All right. So A is in certain cases, 20 mesh is acceptable. Let's say I'm looking for moisture content or protein content or ash content. I need to reduce my particle size to 20 mesh so that I can have accurate results. But if I'm extracting, let's say I'm going to extract fat or even extract protein for further analysis, I need to reduce my particle size to 40 mesh. Okay, you don't know that, you didn't even do guess there. So, not in all cases it's 20 mesh, depends on the experiment. Yes, we want to control enzymatic activity because enzymes can change the composition. So if there are enzymes there, some constituents will be broken down. If you're looking for starch and you have amidases that are active, it's going to break down your starch, you will have very mixed results. So you don't want enzymes to be active. Lipid oxidation, you don't want that either, because also if you're looking for stability or fat stability over storage, and you have stored your samples under control condition, then you take out the sample from your storage, and then you prepare it for the analysis. If during preparation you induce lipid oxidation, then your whole shelf life study will be messed up. So we don't want any lipid oxidation. You don't want any chemical reaction basically happen between the time you pull out sample for analysis until the time it actually run the analysis. Because sometimes there are some preparations that takes long time to do the whole preparation steps. And sometimes the analytical procedure is very long. So between preparing the sample and actually running the experiment, there might be time. So you want to be very careful on how you store your sample, how you prepare your sample. Let's say you want to mill the sample, you don't want to overheat, because that might cause moisture to evaporate. And if you're determining moisture content, you already got made some error that caused an underestimation of moisture because you milled at high temperature, and some of the moisture actually evaporated while you were preparing the sample. So you don't want to have any alteration of the sample by the time you pull the sample out, prepare it, and then run it for analysis. So is it feasible to evaluate all foods or all ingredients from a particular lot? No, because sometimes a lot means several, maybe thousands of cans in one lot. You cannot analyze all of the cans, obviously. You want to select some representative samples to be tested. Or let's say you have a truckload of grains. You need to run moisture, you need protein content, you need to run some analysis. You're not going to take all this grain and analyze it. You need to take sample from the population. So unless you need to detect for metal, for glass, for I don't know, little pebbles, stones, so they can run through a belt and do metal detection or sieves to remove the stones or pebbles or whatever you have that are contaminated. So non-destructive way of cleaning or assessing certain characteristic of the entire population. But in many cases, obviously, you need to take samples that are representative of the entire lot. So this is a key word, that I'm taking sample that represents the whole lot, that can help me make a very accurate decision or as close to true decision as possible. So I take a representative sample from the whole lot so that I can accurately estimate the situation or the status of the whole population. And then reduce variance and be sure of my decision. So there is something we call sampling plan. So when students used to do, again, the semester-long project, which you don't have to do anymore, one of the important section of their report is their sampling plan. So how to take a representative sample for testing, that was part of that project. So the sampling plan includes the sample size. When I say the sample size, it doesn't mean the weight or the volume of the sample. It means how many numbers of samples I'm going to pick from the lot to do analysis on. Am I going to take 10 samples? I'm going to take 15 samples. I'm going to take 100 samples. So what is the sample size, or in other words, my replication? Okay. Sampling procedure. How am I going to pull out samples? Is it going to be a systematic sampling? Let's say I have milk going through the system. I can have at certain time points, an instrument is going to go in and pull out 10 milliliter of sample every 2 hours or every 3 hours. That's systematic sampling. Am I going to open boxes and take certain random number of containers from each box? How am I going to do that sampling procedure, basically? And then how am I going to prepare the sample? Am I going to homogenize? I'm going to mill. How am I going to do? What are the different sample preparation I have to go through? And also the plan includes what's the storage condition, under what moisture, relative humidity, temperature. Am I going to put it in a container? Am I going to flush with nitrogen to remove air to avoid lipid oxidation? So what are my storage conditions are going to be? And if I'm transporting, so I'm taking a sample from a particular plant and I'm going to bring it to the testing lab, am I going to transport it on ice? Am I going to transport it in sealed containers? So I need to think of the transportation if it's going from one place to another. So that's your sampling plan. So sampling plan includes all of these subcomponents. Okay, we'll hold this till next lecture. So there is table in your book, chapter 5, table 1, page 64, it kind of gives you factors to consider and questions you answer in order to come up with a sample you can. I put here define. This is one when you study, you want to make sure that you're able to define a sample you can, just as I defined it on the earlier slide. So this is something to think about. If I tell you what's your sampling plan, you know what I will be asking you about. Okay, so things to think about. Why am I doing this inspection? Is this test going to be to accept or reject? Is it just a general quality assessment of my lot? Is it to determine if my production is consistent with the previous production? So depending on the questions I have, it might influence the sample size, sample preparation, and all of that. What's my product is, the nature of my product, is it homogeneous? If it's heterogeneous, I need to make it homogeneous, or I need to take samples from different parts of my product. So just, look through these questions will help you understand better how you would design a sampling plan. So the table goes on to have you think about the tests that I'm going to do. The population, is it large but uniform? It is small, is it how many units do I have? Is it individual containers, or is it just sacks of flour, for example? So there are different categories of sampling. One we call attribute sampling, and the other is variable sampling. So attribute sampling is when I'm looking for a particular attribute or variable that is distributed in a random manner. That means we don't know where it is in the product. It can be on the surface of the product. It can be in the middle of the product. It can be in one can, but not in the other can. So its presence is random and not predictable. We can't predict where that attribute is we're gonna find it. Example, if we are looking for presence of Clostridium botulinum, which is supposed to be 0 in your product after retorting, you shouldn't have any, and you pull a sample a can and you found Clostridium botulinum, what do you do then? So when something you're looking for can be present unpredictably across your samples, then what you need to do, your sample size will be really large, especially if it has to deal with safety and when you have consumer risk. You don't want Clostridium botulinum, you don't want aflatoxin, you don't want any chemical of concern that will potentially cause the consumer to get sick or die potentially. So this is an attribute that is not generally homogeneous throughout your product. It's not predictable. So you take a large sample size. That means you take a lot of different samples from multiple locations to ensure that your product, the whole lot, is safe. So here we are checking presence or absence of a random variable that cannot be predicted of where it could be present, and then we decide acceptability. And here's an example of Clostridium botulinum in canned foods, for example. So basically, an organism or a component of concern that we don't want it to be, we measure it. Is it present? Is it absent? Positive or negative test. Allergen, for example. You must put on the label if it contains peanuts or one of the other big 9 allergens now with sesame being added to the big 8. So you have to put it on the label, so you would do an allergy test. That's another example than Clostridium. So present or not present? If it is present, then you have two decisions to make. No, because you should have zero, that's regulation, you should have zero botulinum. So you would just reject the whole lot. If it is yes, but it's a different organism and you have an acceptable range, then you would say, well, we can accept it if the quantity is within a particular range. So it depends on what you're looking for and the defect that you're looking at and whether or not they're an acceptable limit or amount. Now, the variable sampling, that's more common. That's, for example, looking for moisture content. Or I'm looking for any sugar, glucose content. Anything that is homogeneously distributed in your sample. It's a constituent that is not random. It's not predictable. So in this case, you would just need to have a small sample size. Not necessarily a large number of samples that you pull, a limited number of samples that you take out because your attribute is consistently present in your entire sample or entire population. And usually it's a quantitative measure and you measure it on a continuous scale. So how much is your moisture content or ash content? It's measured on a continuous scale from 1% to 100%, for example, with decimal points in the middle. So continuous scale, and then you decide acceptability based on certain specification, certain quality desired by the company, by the consumers, by government regulations. And then these are examples: color, total solid, salt, the list goes on. All of those components that can be quantitated, and there is a quality or a reference number that you would be attempting to reach or to have. So selection of sample size depends on the expected overall quality and sampling cost. Sometimes you're limited in how much it costs to get samples tested. Sometimes you are limited if you're really worried about hazardous components, you have to take multiple samples, many samples. But sometimes you're really governed by regulations. If it's for nutrition labeling, FDA and FSIS regulates how many samples you should pull for nutrition labeling. Example, for FDA, if you're doing nutrition labeling, you should get 12 individual samples collected randomly. So if you have cans in many boxes, you would randomly select 12 different cans, let's say, combine them and have a composite sample, and then have 6 subsamples or replication. So after you combine all the 12 individual samples, then you do the analysis using 6 replication. We call it subsampling. That is an FDA requirement for nutrition labeling. So you have no control of it. You have to follow regulations. So, okay, this is a little bit lengthy, so I have a minute, so I'm going to stop here and continue on Monday.